What if the Mars we see today, this freezing dry desert world, wasn't always like that?
Hmm.
Imagine it having, liquid water flowing on the surface, maybe even a thicker atmosphere, more like Earth's early days.
It's a fascinating thought,
It
absolutely.
really makes you stop and think, doesn't it? What on Mars could have happened to change things so drastically?
And that's precisely the big question we're digging into today.
Yeah.
We're going to look closely at some, well, pretty exciting recent findings. They come from the Curiosity rover.
Curiosity, okay.
Yeah, and specifically evidence it's found for a past carbon cycle on Mars.
Right, a carbon cycle. So for you listening, if you're keen on understanding these big science ideas, but, without getting totally swamped by jargon, this is for you.
Mm-hmm.
We want to unpack how some, tiny mineral clues found by Curiosity deep inside Gale Crater are basically forcing us to rewrite the history books on ancient Mars. We're focusing on those aha moments.
Exactly. And the basis for our chat today is a recent scientific paper. It details the analysis of data Curiosity collected, specifically within Gale Crater. The rover looked at this 89-meter-thick stack of ancient sediments, a real window into the past.
Okay, so 89 meters, that's substantial. Before Curiosity sent the specific data back, what did we generally think about early Mars? Regarding water and atmosphere.
Well, the landscape itself gives us pretty strong hints. You look at Mars, you see features that look, I mean, unmistakably like dried-up riverbeds, ancient lake basins, too.
Right, the geomorphology.
Exactly.
Yeah.
Suggests water definitely flowed. Now, for that water to stay liquid, that's the tricky part, especially because the early sun was quite a bit fainter than it is now.
So it should have been colder.
It should have been colder, yeah.
Yeah.
So climate models tell us Mars likely needed a much, much denser atmosphere back then, probably rich in CO2, carbon
How
dioxide,
much denser are we talking?
potentially many times thicker than what Mars has now. I mean, today's Martian atmosphere is incredibly thin. It's around, what, 6 millibars of CO2? Almost nothing.
Wow. Okay, so a massive difference between then and now. So Curiosity lands in Gale Crater. Why there, and what did it find in these layers you mentioned?
Right. Gale Crater wasn't just chosen randomly. It has Mount Sharp right in the middle, this huge mountain made of layered rock, sedimentary rock. That's like a geological history book.
Perfect place to look then.
Absolutely. And this particular study focuses on layers rich in sulfates. They're part of what geologists call the Mirador Formation, and specifically members named Contigo, Amapari, and Chenapau. Curiosity sampled rocks at different heights within these layers, kind of moving up through time.
And it wasn't just looking at the surface, right? It actually drilled down.
It did. That's key. It drilled and collected powdered rock samples, four main ones for this study, informally named Kanema, Tapokaparo, Ubajara, and Sequoia, collected on different Martian days or sols.
Okay, so what did the analysis show? What were the minerals inside?
Well, the really interesting stuff came from an instrument called CHEMIN, Chemistry and Mineralogy. It uses X-rays to figure out exactly what minerals are in the powder. And in 3 of those samples, Tapokaparo, Ubajara, and Sequoia Chemin found quite a bit of siderite.
Cyrite. That rings a bell. It's an iron carbonate, FeCO3.
Exactly, iron carbonate. And it wasn't just a trace amount. We're talking concentrations from about 4.8 up to 10.5% by weight in those samples.
10%. That seems like a lot. What was special about this siderite?
Well, what really stood out was its purity. It was almost pure iron carbonate, very little magnesium mixed in, and essentially no detectable manganese or calcium.
Hmm. And that's unusual for Mars.
It is, yeah.
Hmm.
Other carbonates found on Mars before, they tended to be much richer in calcium and magnesium. So finding this almost pure iron carbonate was, well, it was significant.
Okay, so Cheerman finds this pure siderite. Did any other instruments on Curiosity back this up? You need confirmation in science, right?
Absolutely, and they got it from the SAM instrument suite. Sample analysis at Mars, specifically something called evolved gas analysis, or EGA.
How does that work?
Basically, they heat the sample up bit by bit and measure the gases that get released at different temperatures. SAM detected a release of CO2, carbon dioxide, exactly when you'd expect iron carbonate to break down from the heat.
Ah, okay. So the gas coming off matched the mineral Chemin saw.
Precisely. It's strong, independent confirmation. We're pretty confident this relatively pure siderite is really there in those ancient Martian rocks.
Okay, so we've got this nearly pure iron carbonate sitting in sedimentary layers. How did it actually form? And what does that tell us about, what Mars was like back then?
Good questions. The amount of it and its specific composition strongly suggest it formed through sedimentary processes. It doesn't look like it came from, say, hot hydrothermal fluids altering volcanic basalt rock directly.
Which was an idea for other Martian
It
carbonates.
was, yeah. But this siderite seems different. The evidence points towards it precipitating, basically solidifying out of fluids,
Hmm.
probably in environments where water wasn't super abundant, maybe more like wet sediments or shallow ponds where evaporation was happening.
Evaporation. Okay, so maybe not a deep ocean, but something more transient.
Possibly. Or at least environments where water levels fluctuated. You see, for siderite to form, the water needs a certain chemistry, enough alkalinity, a specific pH range, and that's linked to how much CO2 is dissolved in the water.
Right.
What's interesting is the calculations suggest the amount of CO2 needed in the water in these maybe subsurface pore spaces. It could actually have been lower than the amount some theories propose for the entire ancient Martian atmosphere.
So maybe conditions were right for it to form in specific spots, like underground, even if the whole atmosphere wasn't super thick.
That's a possibility, yeah. Localized conditions could have been key. And here's another clue. This siderite is found right alongside minerals that dissolve really easily in water sulfates, like starkite, anhydrite, kieserite, gypsum.
Those sound like things left behind when water dries up, like salt rings around a puddle.
Exactly. Think of them like evaporates. Finding them mixed in or layered with the siderite is strong evidence that evaporation of water in Gale Crater was a major driver for forming these minerals.
So the water dried up and these minerals dropped out.
Pretty much.
Yeah.
And likely in a sequence, siderite isn't super soluble, but those sulfates are even more soluble. So as the water evaporated and got more concentrated, the siderite probably precipitated out first.
Why first? Because it dissolves less easily.
Correct. It's related to this concept chemists call chemical divides.
Yeah.
As water evaporates, the dissolved stuff gets more concentrated. Minerals start to crystallize out, but they do it in a specific order based on their solubility. The least soluble ones come out first.
Okay, got it. Siderite crashes out, then maybe other carbonates, then these really soluble sulfates later as things get really dry.
That seems to be the picture emerging from Gale Crater, yeah. It paints a scene of fluctuating water levels, evaporation. Quite dynamic.
So this is happening in Gale Crater, but what about the rest of Mars? Does this discovery have, like, global implications?
That's the million-dollar question, isn't it? And it's tricky. Because interestingly, when scientists look at similar sulfate layers elsewhere on Mars, using instruments on orbiting spacecraft, they generally don't see strong evidence for widespread carbonates like siderite.
Huh. So why the difference? Is the siderite only in Gale?
Maybe, or
Eh?
maybe not. There are a few possible explanations. One is simple: dust. Mars is incredibly dusty. Maybe thick dust layers are just covering up the signal from these carbonates in other places, hiding them from the orbiters.
Okay, that makes sense.
Another idea is that maybe the carbonates are there globally, but they're mixed in really finely with other minerals, especially the sulfates. That could make them really hard to spot from orbit, even if they're present in decent amounts.
So the stuff Curiosity found by drilling could be hiding just beneath the surface elsewhere.
It's definitely possible. And if that's the case, well, it could mean there's a huge, previously unrecognized reservoir of carbon locked away in these sulfate deposits across Mars.
A carbon reservoir. How much are we talking?
The researchers ran a couple of scenarios. Scenario one: assume this 89-meter section Curiosity studied is just, a brief period when conditions were right for siderite. If you extrapolate that just to the known global sulfate deposits,
Yeah.
you could have locked away the equivalent of about 2.6 to 5.7 millibars of CO2 from the atmosphere.
Okay. 2.6 to 5.7 millibars. How does that compare to now?
It's roughly in the same ballpark as the entire Martian atmosphere today. Remember, the current atmosphere is about 6 millibars. So even this conservative estimate suggests the past atmosphere that held significantly more CO2 just in this one form.
Wow. Okay. And what was the second scenario?
The second scenario assumes that maybe siderite isn't just in that 89-meter chunk, but perhaps it's common throughout the entire thickness of these vast sulfate deposits globally.
Which would mean a lot more carbon.
A lot more. In that case, the estimate jumps to potentially 16 to 36 millibars worth of CO2
Yeah.
locked away in siderite.
36 millibars.
That's up to 6 times the CO2 in Mars's entire atmosphere right now.
6 times. That would make a real difference to the ancient climate, wouldn't it? More pressure, maybe warmer temperatures.
It certainly would have helped. A thicker atmosphere means more pressure, which helps stabilize liquid water, reduces evaporation. And CO2 is a greenhouse gas, so yes, it contributes to warming. It probably wasn't the only factor needed to keep early Mars warm and wet, but finding this potential carbon sink is a really big piece of the puzzle.
a potentially massive amount of CO2 stored away. But the story doesn't quite end there, does it? I remember the paper mentioned something about this carbon being recycled.
That's right. It's not just about forming the siderite. There's also evidence it got destroyed later on. Remember those 4 drill samples?
Kanema, Tepocaparo, Ubajar, Sequoia.
Yeah. Well, 3 of them had siderite. But one, Kanema, didn't. Instead, Kanema was rich in different iron minerals, iron oxyhydroxides, things like hematite and goethite. Basically, fancy names for types of iron rust.
Rust instead of carbonate.
And even in the samples with siderite, the amounts varied. And other minerals pop up too, like acaginite in the Sequoia sample, another iron oxyhydroxide.
So the minerals are different even in samples relatively close together. What does that mean?
It strongly suggests that after the sediments were laid down and the siderite formed, something else happened. A process called diagenesis change is happening within the rock after deposition.
Okay. Like chemical reactions happening underground over time.
Exactly. The idea is that later on, maybe different kinds of fluids, perhaps sulfate-rich waters that weren't saturated with carbonate, flowed through these rock layers.
And what would those fluids do?
They could react with the existing siderite. They could dissolve it, break it down, and in the process, they'd form these iron oxyhydroxides, the rust, and, crucially, release the carbon that was locked in the siderite back out as CO2.
Ah, so the carbon goes back into the environment, maybe even the atmosphere?
Potentially, yes. It's like a chemical weathering process happening underground. And there's a bit more evidence for this, too. The SAM instrument detected faint traces of iron sulfates, which are exactly what you might expect to form during this kind of siderite-destroying reaction.
Okay, so evidence for both formation and destruction. Is this just a Gale crater thing, or have we seen hints of this elsewhere?
That's what makes it even more compelling.
Yeah.
Scientists have seen similar patterns, evidence of older carbonates seemingly being altered or destroyed, leaving behind iron oxides or oxyhydroxide in other places on Mars, like in the huge canyon system, Valles Marineris, and in Terra Meridiani, where the Opportunity rover explored.
Really?
Yeah, and even in Martian meteorites that have landed on Earth. And interestingly, similar diagenetic processes happen in sandstones right here on Earth. So it looks like this destruction of carbonates might have been a pretty widespread process on ancient Mars, not just a local fluke in Gale crater.
So putting it all together,
Yeah.
formation, then destruction. It sounds like ancient Mars actually had its own kind of carbon cycle going on.
That's the major conclusion, yes.
Hmm.
The evidence points to, let's say, a partially closed carbon cycle. You had CO2 being pulled from the atmosphere, sequestered into carbonate minerals like siderite through these sedimentary processes, likely involving evaporation.
Locked away in the rock.
Locked away. But then, later on, diagenesis happens. Fluids move through, break down some of that siderite, and release some of the CO2 back out again.
So it's cycling, but you said partially closed. What's the catch? Was it different from Earth's cycle?
That seems to be the critical difference. Earth has a complex but over long time scales. Relatively balanced carbon cycle involving volcanoes, oceans, life, plate tectonics. It keeps things reasonably stable.
Right.
The Martian cycle described here seems to have been, well, imbalanced. The fact that we still find significant amounts of siderite in these ancient rocks billions of years after they formed.
Means not all of it got destroyed and recycled.
Exactly. It suggests that ultimately more carbon was getting locked away into minerals than was being released back into the atmosphere through this diagenesis process.
So the sink was bigger than the source, eventually.
It looks that way. This imbalance, this tendency for Mars to trap its atmospheric carbon dioxide and minerals over geological time.
Mm.
That could be a fundamental reason why Mars lost its potentially thicker, warmer atmosphere and evolved into the cold, dry planet we see today. It's a crucial insight into planetary evolution.
Okay, so let's try and boil this down. The really big picture here for you listening is that finding this specific type of iron carbonate, siderite, and figuring out how it likely formed and then partly broke down again inside Gale crater,
Yeah.
it's a huge piece of the puzzle.
Mm.
It helps us understand the history of Mars's atmosphere, its water, and the potential for past environments where, maybe life could have existed. Mars wasn't just static and dead. There was dynamic chemistry happening.
Definitely. And it leaves you with some big thoughts to chew on. Like, consider this. If Mars had this more active carbon cycle than we perhaps realized, even if it was imbalanced,
Yeah.
what does that tell us about how long liquid water might have really persisted on the surface?
Good question. Could water have been around for longer or in more places?
Potentially. And maybe the bigger question, could this very imbalance in the carbon cycle, the fact that Mars seems better at locking carbon away than releasing it,
Yeah.
compared to Earth, be one of the key reasons why these two planets, which might have started out somewhat similarly, ended up so incredibly different.
That's a profound thought. Why one planet stayed habitable and the other didn't.
Wow. Well, if this deep dive into Martian rocks has got your curiosity going,
Yeah, nice one.
then the original scientific paper has loads more detail. You can really get into the weeds on the mineral analysis and the geochemical models they used. It's truly fascinating stuff, seeing how we piece together the story of another world, basically one rock sample, one mineral grain at a time.